There we go. I think we're recording now. All right. So anyways, let's go ahead and get started with the math here. So today is our first actual day of content. Remember last time I was kind of giving like an overview of the class, and the first part of this class is going to be about integrals, which is kind of where we left off with Calculus 1. So for today's lesson, we're going to start learning about more integration techniques. Today's lesson is about U-substitution and integration by parts. So hopefully you guys have at least seen this before. Has everyone seen U-sub? Is this something you covered in Calculus 1? Okay. All right. And then this is going to be something that may be new for some of you guys as well. All right. So before we do anything, I just want to kind of go over some basic Calc 1 integrals just to kind of get ourselves back in the integrating mood here. One of the easiest things to integrate is x to a power, like x to a fixed power n. And let's see if everyone remembers this. The way we do this is we just raise the power by 1 and then divide by the new power. And is that it, or is there something else? Plus c, that's right. Thankfully, you guys are going to have all your stuff online, so you won't actually need to remember the plus c, so you guys got lucky with that. But yeah, there's always a constant when there aren't bounds on the integral here. And this is true for any n not equal to -1. If n is equal to -1, meaning we have 1 over x, what is this one going to turn into? You guys remember what this is going to be? Natural log, that's right. So it's natural log, and then we can't forget that there's actually an absolute value. Oh, okay, make sure you mute yourself. It sounds like the voice of God in here, so be sure you're muted. Okay. All right, yeah, so we can't forget about the absolute value here. And this is a very common integral. We're going to see this quite a bit. So let's go over some basic trig integrals here. So we have the integral of cosine, that's going to be sine of x plus c. And then we have the integral of sine of x, and that one's going to be negative cosine of x plus c. So the negative is on the reverse 1 as it was with derivatives. All right, and then one other one we have, which is probably the easiest integral to do, e to the x. What's the antiderivative of e to the x? E to the x, that's right. All right, so we got e to the x plus c here. One thing I'm not entirely sure if they went over in Calc 1, this one's kind of hit or miss. We can also integrate other exponential functions as well, not just with base e. Does anyone remember how to do that? What's the formula for this, the integral of this? That's right. So there's going to be a natural log of a in there. We're going to divide by it. That's right. So this is for a greater than 0 and a not equal to 1. So this is something we won't see too often here, but it does show up from time to time. So I guess it's good to be aware of it. And then there are also two properties of integrals that we learned in Calc 1, and these we kind of just take for granted. So I'm just going to mention them, and then we'll take them for granted forever. So if we have the integral of two functions added or subtracted, then we can simply do the integral of each one of them on their own. And that's something we kind of barely even think about. We're so used to splitting up integrals over addition and subtraction. And another thing we kind of take for granted is that if we have a constant times a function, or if we have a constant in our integral, then we could just move that constant out to the front. All right. Now, these facts right here, so make sure you guys are comfortable with these, because I'm going to be I don't really show too many steps when we're doing integrals like this. I'm going to assume that this is stuff that you have good experience with in Calc 1. If you do feel a little bit rusty on this, I recommend kind of going over it as soon as you can. And if you feel stuck, feel free to email me. I can help you out with that. All right, anyway, so this is all Calc 1 territory. So let's just do an example just to get ourselves warmed up using these rules. Example 1. Let's do the integral from 1 to 2 of 4 over x squared plus 2 to the x dx. Okay, so remember, this is called a definite integral. We do it the same way we do an indefinite integral, but then we plug in some numbers at the end. All right, so let's see. This right here, if I have an x squared on the bottom, this is technically x to the negative 2. So that means that we can use the power rule on this. So if I use the power rule on this x to the negative 2 here, I raise the power by 1, and I get negative 1. So I have 4x to the negative 1, but then I have to divide by my new power, which is negative 1. All right, and then we have 2 to the x over here. That kind of falls into this category right here. So this is going to be 2 to the x divided by natural log of 2. Now for definite integrals, remember that we don't need to put plus c on those. We instead put this, what's called an evaluation line or evaluation bar, and we put our bounds there. Now what this is telling us to do is we're going to plug in 2. So I have negative 4 over 2, because 2 to the negative 1 will go to the bottom. And then I have 2 squared over L of 2. Then what I do is I subtract, and I plug 1 in for this. So if I plug 1 in here, I'm going to have negative 4. And if I plug 1 into here, I'm going to have 2 divided by natural log of 2. All right, and I guess I could simplify this maybe a little bit here. I have negative 4 over 2 is negative 2, and then I add 4, so I end up having positive 2. And then this is 4 over ln of 2 minus 2 over ln of 2. It's going to be 2 over ln of 2. So there we go. There's our result from that definite integral right there. So hopefully that was kind of good warm up, stretch your muscles a little bit. All right. So another thing we learned about in Calculus 1 was our first topic of our lesson here is U-substitution. All right, so let's remind ourselves what U-substitution is. We replace one part of the integral with a new variable u. And then we hope that the new integral is easier. That's the primary use of U-substitution, is to make integrals doable in the cases where they may not be. And U-substitution actually has a lot to do with the chain rule. U-substitution is effectively the integral version of the chain rule. It's often used when something is plugged into something else. All right, now, one tricky point that we're going to be experiencing throughout the beginning of the semester is, how do I know which techniques to use when? And for U-substitution, the question becomes, how do I know when I'm given an integral what I'm supposed to make u? And in general, there are kind of 2 tips for picking your u. So here are your tips for picking u. So the first tip is actually, this is really obvious, I think. U should show up in the integral. We usually don't want to pick u as something that's not in the integral. So for example, and actually this, I'm going to add something to this, especially more than once. So for example, if you see an integral and there's like a sine of x plugged into a function, and then there's something multiplied by sine of x, a bunch of signs everywhere, that's kind of a hint that you should maybe do u equals sine of x. So if you see something appearing all over the place in an integral, that's a good opportunity to make it a u. My second tip is a little bit less obvious. The derivative of u should be in the integral as well. Okay, well, why is this the case? Well, let's say we make u some function, right? And this function shows up in our integral. Now, there's something else that we have to do in addition to putting u in. Does anyone remember what else we have to do whenever we make a u substitution? There's something extra. That's right. So the audience members and the chat saying we're going to take the derivative of this. So we have du dx is f prime of x. And if we want to get the differential part of our integral, then we rewrite this as du is f prime of x dx. Now this stuff was the old stuff that was already in our integral, and this is the new. So because of this fact, we want to make sure that the derivative of our u is in there as well, because we need that in order to get our new differential right here. So we also want to make sure the derivative's in there too. All right, so why don't we just see some examples here? There's definitely something best learned through examples. Oh, sorry, bottom of the page cut off. Okay, you can see everything now, is that okay? All right, and you guys in the audience can tell me this too. All right, so let's go to our example. Okay, so what I want to do is I want to do the integral of tangent of x. Now this may be something that you memorized in Calc 1 or you learned how to do in Calc 1, but we're going to kind of do it from scratch right here. We're going to see where this formula comes from. Okay, so there's a way that we can rewrite tangent. We're going to rewrite tangent as sine over cosine. That's how most people think of tangent. It's just sine over cosine. All right, now let's see here. What we're going to do is we're going to try to pick a u for a u substitution. So let's see here. We kind of have two options, or two obvious options, it seems. We can make u be sine, or we can make u be cosine. Which one of those do you think would be better for this situation? Cosine, that's right. So we're going to do u equals cosine. And why is it cosine? Why can't we do sine? Well, let's look at the derivative here. So du will be negative sine of x dx. And lo and behold, we have a sine of x dx already there. If we did it the other way, we'd have cosine of x dx, but we need whatever is in our differential here to be on the top. And cosine being on the bottom wouldn't cut it. So we need to have our du being sine right here. Also, I don't see a negative in this integral, so I'm going to move the negative over. So I have negative du is sine of x dx. And in general, I want whatever I end up with over here to be in the integral. So I didn't have a negative in my integral here, so I moved that over to the other side, and then now this is okay. All right, so what's my new integral going to be? Well, I have sine of x dx, that's equal to negative du. And then on the bottom here, I have cosine, which is u. So this is negative the integral of du over u. And this is one of the ones we just talked about. If we have the integral of 1 over a variable, it's going to end up being natural log of absolute value of whatever that variable is, and then plus c, of course. And then finally, with any u substitution, we can't just leave it in terms of u. We need to turn everything back into x's. So we have negative ln of absolute value of cosine of x, and then we have plus c. Hey, I hate to call you out, but would you mind putting your mask back on? Yeah, thank you. All right, anyway, so this is going to be our integral of tangent. And another way you might see this, so this might look unfamiliar to some people, another way you might see this is natural log of absolute value of secant of x. And it turns out that these are actually the same thing. Does anyone know why these are actually the same function? Yeah, because secant's 1 over cosine, and moreover, we could put this negative into here, ln, and make it the power. So any coefficient in front of a log can become the power, and then 1 over cosine is secant. All right. Very good. So we got that example done. All right, let's take a look at another one here. Let's take a look at another u substitution. Let's see. I'm done with this now. All right. Let's try the integral of x e to the x squared. All right, now I'm going to let you guys think about this. What do you guys think a good u for this one would be? X squared, that's right. So it satisfies the first tip that I said earlier because x squared does show up in the integral, but it also satisfies the second condition, where if we look at the derivative and then divide by 2, that's no big deal, we see this showing up in our integral right here. And whatever we have on this side, we want to be in the integral so we could swap it out when we switch to u's. All right, so that's a good choice for a u substitution here. All right, so let's see. Let's turn everything in here into u's. So we have 1/2 du is x dx. So 1/2's a constant, so I'm just going to keep it on the outside here. And then the x dx will both become a du. And then I have this e, that doesn't change at all. And then I have x squared, which is u. All right, and then if we look at the difference between these two integrals right here, we have this one, which we don't really know how to do because we don't know how to integrate functions multiplied together very well. But then now we just have the integral of 1 exponential. And the integral of e raised to any variable is just going to be itself. And then finally, we can't forget to put back in the x's. So there we go. By the way, a lot of you probably already know this, but one way to check your work whenever you're doing an integral is you should be able to take the derivative of whatever you got and end up back where you started. So if you ever want to check your work, an easy way to do that is just take the derivative and hope you get back where you started. All right. Now I said that today we're going to start doing class participation stuff. So that's going to start right now. I'm going to explain how this works. So each class, there's going to be 1 or 2 questions that I want you guys to work on. And I'll give you guys a few minutes to kind of just do that on your own. But you're free to talk to each other. You're free to work with each other. You're free to look up stuff on the internet. Anything's fine. You can ask me questions as well. I just want you guys to get a little bit of practice. And then after a few minutes, we'll go over the problem. And then on Canvas, you'll enter in the correct answer. So there's going to be a Canvas quiz that has these problems in it. I'll show you how to get that once I write it down. So I want you guys to start working on the integral of cosine of ln of x divided by x. All right, so I'm going to give you guys a few minutes to do that. And where is this, this Canvas quiz? So we go to our Canvas page right here. Actually, let me make sure my online people can see it. Can everyone see this on who's in the chat? Okay, good. All right, so this is the front page of our course. Then we go to assignments. All right, and then today's January 13th. We click on this. And then I think you guys will have something to actually take the quiz. So you click that and you'll take the quiz. Now, if you enter in the answer right now, keep it open because we're actually going to have another question later on. And if, for those of you in person, if you guys don't have a computer, don't worry. Just write the answer down and you can submit this when you get back home because the deadline's at midnight tonight. So you guys have a lot of time to enter this in, even if you don't have a computer with you. All right, anyway, so let's go ahead and get started with that. Yeah, why don't you guys work on this integral for a minute or two, and then we'll go over it. Will you submit as a PDF? You know, it's all multiple choice. So you just need to type in, or you just need to click the correct answer. Yeah, even if you get the answer, don't submit this until the end of class because there's going to be another question that we're going to work on a little bit later. And you only get 1 submission for the quiz, so I don't want you to send it in with only half your stuff in. when math has just become letters and no numbers. When I was in math grad school, it eventually came to the point where my homework was essentially just writing essays about different math topics. So like it gets even more and more letters as you go along, unfortunately. I know it's hard in the physical room to work together, but you're welcome to like maybe turn around or talk to someone if you want. I know it's kind of hard with the distancing. Where'd I go to grad school? I went to Kansas State University. So it's a long way from here. Yeah, looks like the chat's going in the right direction. All right, seems like the chat has a good idea. If you're still working on this, feel free to keep working on it, but I'm going to kind of at least get this started with. So we're talking about U-substitution, so we should probably try to use that here. Now let's try to find a good U. Maybe we could do cosine of ln of x, that might work. We could just do ln of x or 1 over x. I think ln of x would be the best because it shows up in the integral. That's kind of the no duh condition. But then also, if you take the derivative of ln of x, it's 1 over x. And it may not look like it at first, but we technically have that as part of our integral right here. So I'm going to use u is ln of x, meaning the du is 1 over x dx. And this time, unlike a lot of the other examples, I have exactly this in my integral. So I don't need to do any algebra like I've done for the other ones. All right, so let's change my integral over. So I have cosine of ln of x, and that's going to be cosine of u now. And then 1 over x dx, that simply turns into a du. All right, so now we're back to Calc 1 here for sure. We're just going to do the integral of cosine, and that's going to be sine of u. And remember, the integral of cosine is positive sine. It's the opposite as it was for derivative, so there's no negative here. And then finally, we put back in what our u is, and so we have sine of natural log of x plus c. All right, so for anyone with Canvas open, feel free to click that box right now, because that's what it's going to be. But don't submit your quiz yet, because we still have one more question later on. I'll let you know when it's okay to submit. All right, awesome. So that's U-substitution. So this is kind of been a review of Calc 1 stuff. Now, let's go back to this example right here. X e to the x squared. I think I said this while we were doing it. There's not a nice way for us to do the integral of two things multiplied together. We didn't learn about anything like that that would allow you to do so in Calc 1. But one thing you might be thinking, oh, can I just split the integral up? Like, can I just do the integral of x and then the integral of this? And unfortunately, the answer to that is no. And to kind of drive that home, I want to show you kind of like a bizarre example of why that goes wrong. So let's say I want to do the integral of x squared. And we actually already know what this is going to be, so we can easily check our work. What's the integral of x squared going to be? Yeah, x cubed over 3. And then I could write the plus c if I want, but this is still an acceptable antiderivative here. So I'm going to skip the c's for now. Now, last I checked, x squared is x times x, right? Now, if I split the integral up over multiplication, and I'm going to put quotes on this equal sign because we can't actually do that. But let's see what happens if we try. So we have each of these, right? Now, what's the integral of x going to be? Yeah, 1/2 x squared, right? And we have two copies of that. So we have x squared over 2 times x squared over 2. But if we combine that, we get x to the 4th over 4. And as you can see here, we know this is the answer, but then we end up getting this as the answer right here. So this is kind of a demonstration as to why we cannot split up integrals over multiplication. And another way it kind of makes sense is that we weren't able to do that with derivatives, right? And derivatives are more or less the opposite of integrals. So it kind of makes sense that integrals won't have that property either. So if you're ever in doubt about splitting up integrals over multiplication, just remember this kind of bogus example right here. This is bad. This is frowny face. So we don't want to do that. All right, so how can we actually integrate functions that are multiplied together? We use multiplication a lot in math, so we should be able to deal with it. What we're going to do is we're going to draw inspiration from the product rule of derivatives. So let's say I have two functions. And for a reason we'll see later, I'm going to call these functions u of x and v of x. Although you could also do this with u and, f and g as well. All right. So if we wanted to take the derivative of these multiplied together, does everyone remember what this is going to be? What's the product rule for derivatives? That's right, yeah. So we have du dx times v, and then we have u, and then we have dv dx right here. All right. So now what we're going to do here is we're going to integrate both sides of this equation. If these are both the same function, then they should have the same antiderivative, at least up to the plus c. So what I'm going to do is I'm effectively just going to integrate both sides of this. Now notice what I'm doing here. I'm finding the antiderivative of a derivative. So what's going to happen on the left side here? I'm doing the antiderivative of a derivative. They're going to cancel out. That's right. That's what we learned in the fundamental theorem of calculus, is that integrals and derivatives are in some sense opposites. They're going to cancel out. And that's exactly what's going to happen here. So these will cancel out more or less. And then we have u times v. And then meanwhile over here, I'm going to have the integral of v du dx times dx. And then I have the integral of u dv dx times dx, because I'm doing this integral with respect to x. All right. Now let's see here. If I have du over dx times dx, now remember, derivatives aren't quite fractions, but they do often work the same way that fractions do. So if I have u times v over here, this is going to simplify into v, and then now I'm doing my integral with respect to u. And then something similar happens with the v. I have the integral of u, and then I have dv. This may be looking familiar to some of you guys who maybe took BC or something like that. What we're going to do for our last step is we're just going to subtract this over here. So we have uv minus the integral, oops, we're out of room here. So we have uv minus the integral of v du is the integral of u dv. And this right here is called the integration by parts formula. And I don't want to write that every single time. I'm going to always call this IBP, for integration by parts. Okay, now it may be kind of confusing because we're used to using f and g's for our functions. So what is this actually saying? What this is saying is that if we can split up our integral into two pieces, u and dv, you can rewrite it like this, where there's stuff that's not even in an integral anymore, and then you have a different integral. So why do we want to do this? The goal is to take this, which could be a hard integral, and replace it with just a function. We don't even need to do anything with that. And then we hope that this is going to be an easier integral. This is the whole idea of integration by parts. We split it into two pieces, our hard integral, and then we are hopefully going to turn it into something easier. If it doesn't become easier, then maybe we shouldn't use integration by parts. All right, so that's kind of, this is going to be our closest approximation to a product rule that we're going to have here. All right, so let's do an example of this. Let's get practice with this. Example 4, find the general antiderivative of x times sine of x. All right, let's see here. So we're doing the integral of x times sine of x. That's simply another way of saying the general antiderivative is having an indefinite integral. And now what we're going to do is we're going to use the integration by parts formula here. Now that requires us to make a choice. We need to break up our integral into 2 pieces. Now, whatever we pick for our u, we're going to end up doing a derivative of that. And whatever we pick for our dv, we're going to end up doing an integral like that. So whatever we pick, in particular for our dv, whatever we pick here, we need to make sure we know how to integrate it. And for the derivative here, we want to see if it gets easier or simpler as a function as we go along. So in this case, I'm going to pick my x to be my u, and I'm going to pick my dv to be sine. I know how to integrate sine, so that's a good choice for dv. And then I know if I integrate or differentiate x, the derivative of x is 1. And this is how we get du. And then how do we get regular v? We do the integral of sine of x here. And what's the integral of sine of x? Is it positive or negative cosine? Negative cosine. All right, so we do the derivative of u to get du, and we do the integral of dv to get v. All right, so now that we have all of the pieces to this, let's go ahead and use the formula. So the integral of u dv is u times v, not even in an integral. So we have negative x cosine of x. And then we subtract the integral of negative cosine of x times, and then that's just a dx here. Pay attention to this negative sign. This is probably one of the easiest negative signs to miss in the world. This is probably the one that I miss the most. So don't forget that the integration by parts formula has a negative by default. Don't forget about this negative here. Okay, now remember, our goal is to make the integral that we get out of this easier. And let's see if we have accomplished that. The negative of a negative will be positive, and we end up with the integral of cosine of x. And lo and behold, that is a much easier integral than the one we started with. So now we could just go back to Calc 1 to finish this off. The integral of cosine of x will be positive sine of x. And now that I'm totally done with all my integrals, I can go ahead and put plus c. All right, so this kind of illustrates the power of integration by parts. We could take something that we don't know how to work with and turn it into an integral that's easier, plus some extra stuff here. All right. Let's see here. I'm going to do one more example, and then I'm going to give you guys one to do. Well, actually, let's see how we're doing on time here. Oh, we're doing great on time. Awesome. All right. So I'm going to do one more example. Then I'll give one for you guys to do. Okay, so I'm going to integrate t e to the t dt. In addition to x, t is a very common variable, so we should get used to using that. Actually, there's a question here in the chat. Why is x cosine of x negative when you plug the u back in? It was negative because we got a negative sign from this integral, and then we do this times this. And the negative sign kind of carried on to that. That's where that negative comes from. All right, anyways, let's go ahead and get started with this. So we have 2 functions multiplied together. That's a good sign that we're going to use integration by parts. We won't always do it for 2 functions multiplied together, but we will quite a lot of the time. Now, in order to use IBP, we need to pick a u, and we need to pick a dv. So let me ask you guys, both in person and in the chat, what do you think I should pick for my dv? E to the t, that's right. And then that means we're going to have t over here. And you notice that I had the polynomial be my u here, And it also ends up being the polynomial here as well. And that's no coincidence. Most of the time, we're going to end up having our u be a polynomial if one does appear. I emphasize, I say most, not all the time. There'll be some exceptions, but most of the time, we're going to have u be a polynomial. All right, so now that we've picked this, let's do the derivative. The derivative of t is just 1. And then we're going to do the integral. The integral of e to the t is e to the t. And then now we can go ahead and use our formula right here. So we have u times v. That's going to be t e to the t. That's our uv. And then we have the integral of v du. So we have e to the t, and then we have du. Wait a minute, what am I saying? It's dt. There we go. There we go. So this is u times v, and this is the integral of v du right here. And once we do this, we need to ask ourselves the question, did we accomplish our goal? Did we make our integral easier than it was before? And did we do that this time? Is e to the t an easier integral than before? Yeah, absolutely. It's one of the easiest integrals. It's just going to be itself. And there we go. So another successful integration by parts here. Now, in Friday's class, we're going to see that sometimes we may need to use integration by parts more than once. Like we get an integral that we still can't quite do, but maybe if we do integration by parts another time, or maybe even 2 more times or something, then it'll eventually turn into something we can do. But that's more for next class here. All right, so now I want to give you guys your second practice problem here. So I want you guys to give this a try. Practice 2. Okay, so what I want you guys to do is do this integral. The integral of x squared ln of x. All right, so why don't you guys give that a try? Why don't you try to use integration by parts for that one here? Yeah, I'm sorry to the online people that it's staticky. I don't know how to fix that right away, but hopefully it'll be fixed by next time. How do we choose which one is u? You got to think which one is better to differentiate. Honestly, I would always pick my dv first because it's harder to integrate than differentiate. So if one of them is going to be impossible to integrate, you need to make that one u because you can't integrate it. So pick your dv first. Now we got an answer already. We'll see if that's right in a few minutes. I'll give you guys maybe another minute or so, and then we'll go over this. All right, I think we're seeing pretty consistent answers in the chat. Let's go ahead and see what's going to happen. So I think this is going to be an integration by parts thing because I don't see an obvious U-substitution to do because the derivative of this is 1 over x. Yeah, I think U-substitution is kind of out. So the only option we really have at this point is do IBP. All right, so that means we need to pick a U and a dV. Now, I think we have a little extra time. Let me show you what's going to go wrong if we do it the wrong way. So it seems like we've had a lot of success picking polynomials as our U, right? And most of the time that will be successful. But let's try that here and see what happens. All right, so let's say U is x squared, dV is L of x. All right. So du, let's see, that's going to be 2x dx. Okay, that was fine. All right, v. So if we need to figure out what v is, that means we need to know the antiderivative of natural log of x. So does anyone know what that is? Anyone know that? I don't think that's something they usually go over in Calc 1. Yeah, it turns out that typically the way you get the integral of ln of x is doing integration by parts. And we'll actually see that as an example next class. But in general, doing this integral is actually a little bit tricky. So we don't really want to go that direction. Yeah, it looks like in the chat that some people do know the answer. The integral of this is x ln of x minus x plus c. That's totally right. But if you put that into your v right here, the IBP formula will actually make the integral worse. So even if you did know what that is, it's still not a good idea to do it. All right, so this did not work out. So let's try it the other way. And sometimes that may happen. Sometimes you may pick the wrong substitution. Sometimes you may pick the wrong thing for your dV. And that's okay. Once you see it's not going to work, just try to pick something else instead. All right. So this time I'm going to have it be the other way. U is ln of x, dV is x squared dx. All right, this time du, the derivative of ln of x is going to be 1 over x, and we have dx. V, I do the integral of this, so I have x cubed over 3. And then now I can do my formula. So my original integral right here is going to be u times v. So it's x cubed over 3 ln of x. And then I subtract, and then I have v du. That's 1 over x times x cubed over 3. All right, now if I simplify my new integral here, I cancel out one of the x's, and I have the integral of x squared over 3. And let's do our check here. Is this integral easier or more simple than the last one? And the answer is definitively yes. This is one we can easily do back in Calc 1 with the power rule. And that's exactly how we're going to finish it off. So we have x cubed over 3 ln of x. And then we raise this power. Oops, thank you. A lot of times I just get sucked into it, and then I totally forget that I'm streaming this. So anyways, we're integrating x squared here. So we're going to raise that power to be 3, and we're going to divide by the new power. But we already had a 3 we're dividing by, so that means in total we're dividing by 9. And this right here is going to be our answer here. Now, if I remember correctly, I don't think that's the one that shows up on Canvas. I think Canvas has it factored. We can move an x cubed out of 3, or x cubed over 3 out of both of these terms. So if we do that, we're just left with ln of x here. And if we do that for this part, we end up with 1/3 because we had a 9 down there. So this is also an acceptable answer. One issue So one upside of the class is that you don't have to remember things like plus C since it's all multiple choice or type in your answer. The downside is that sometimes you may get a correct answer on paper, but it may not appear as a multiple choice option. So for example, maybe you got this as the answer and it's correct, but this appeared in the multiple choice. So that's kind of the downside of having online exams. You need to be comfortable manipulating this to see that it's really the same thing as one of your answers. So I recommend practicing simplifying if you feel a little bit rusty with it. All right, let's see here. Well, it looks like I got to the end of my lesson. Usually, I'll say one thing. Usually we're going to end up running out of time rather than not the other way around. So I guess take this as a blessing. So yeah, next time we're going to learn more things about what we could do with integration by parts. It is more than just a product rule for integrals, and we'll be doing a bunch of that next time. So yeah, I will see you guys on Friday. And for those of you in the chat, if you have a question, feel free to type it in the chat now, and I can try to answer it. And of course, people in person can come up and ask me a question if you want. You don't have any homework tonight? No, there's no homework tonight. The first homework's to do on Friday, which is Chronos Homework 0, which is just a tutorial on how to use it. Yeah, see you later. You could like come like up to here or something. Yeah.
My issue wasn't like not understanding, it was just not being fast enough and accurate enough with it. But you gave us the 4-function calculator, and I'm so excited because I'll actually be able to like.
Yeah, you don't need to worry about the arithmetic. Yeah.
Yeah. Okay. I'm really happy about that. Could you go over the power rule really quick with the last question?
Yeah, sure. So we simplified this integral because we were able to cancel out an x on the bottom here, and this reduced to x squared. So if we're going to do this integral in detail, technically one thing I do, but I often don't write this, is I moved out this constant. This is a 1/3. So I move that out.
Oh, I see it now.
And then what I do is I raise this by 1 to get 3, and I divide by 3. So this is 1/3 times another 1/3, and then now I have an x cubed. And then these combined to give me that 9 down there.
Okay. Do you have any like resources to practice like U-substitution from like Calc 1 and stuff? Like I don't remember that one.
Were you the one who emailed me about? Did you email me? Okay, someone emailed me asking exactly the same thing. If you do email me with it, I could send you a link to some resources and websites and stuff.
Because that was like one of the last few lessons, and I just didn't absorb. Okay. Anyway, thank you.
Hey, sorry guys, I gotta pay attention to the chat here. I'm sorry guys, it's really hard to split my attention here. Where do we find the recordings for the lectures? Since we now, oh, I forgot to turn off the recording.